Ellis, KJ6 PWP. I'm going to be talking a little bit about the project here today and hopefully answering any questions you might have throughout here. So a little bit about myself. I'm an amateur extra class operator. Been licensed since 2011. I got my extra class license in 2016. I've got a real interest in my kind of ham radio hobby experience working on broadcast transmitters, and that stems from working on old boat anchor and military radios with my grandpa. I have a lot of interest in repurposing things and homebrewing stuff, figuring out ways to make something out of nothing and find use for things that would otherwise maybe be going to the dump. I'm a master's of electrical engineering student at Sac State with a telecommunications focus, which was great because I got to incorporate the hobby into my studies there. And then for work, I'm the electrical quality assurance chief at Caltrans for roadway materials, electrical stuff. So going into the ham background here, oh, actually, you know what, I missed something. So to describe the picture here, so this is actually one of the broadcast transmitters that I've collected over the years, and this is a pre-World War II RCA kilowatt transmitter. So there's a 250 watt exciter on one side and a kilowatt amplifier on the other. There's actually an interface panel that goes in the middle, is not shown in this picture, that provides all the power supply mounting for the low level stuff. But this is one of the cooler ones that I was able to acquire throughout the years. And hopefully the topic of a future conversion. So going back to this one here, my whole life I've been working on ham radios. I've been able to spend from when I was very small tearing apart radios and just cutting wires and having no idea what I was doing, to later on in my career and in my experience in the hobby getting really more technical on building and designing things. A lot of the times it was going to swap meets, picking up something that doesn't work, and tearing it apart, fixing it, and then selling that to buy the next project. And that was really what educated me on how to work on radios, how to design components, and how stuff that was designed originally worked so that you could make modifications. You could make useful components out of stuff that wasn't useful in the whole system. And it really led to me pursuing my education in electrical engineering and finding out more of the why, the background on the electrical components. So I've created kind of I call it a collection, maybe it's more of a hoard, but of old radios, and I really enjoy taking things and having stuff that you can pull off the shelf and use, but it's also kind of a piece of art and history to maintain. So I've got some of my radios there, a T368 AM transmitter, and then my HT32B is my favorite transmitter to run, and a couple of receivers there as well. So the project background, one of the things is broadcast transmitters of this era, between really the 40s and 80s, are coming up for sale or for free on different venues, Facebook Marketplace, Craigslist, local ham nets. And so it really brought to my attention, you know, is this something that we could use? Solid state equipment from a broadcast transmitter and station side makes way more sense. It's power efficient, it's reliable, it's easy, it's half the weight, if not less. So from a commercial standpoint, there really isn't a point in having a tube backup transmitter anymore. And the BC1T that's shown in this picture that was the guinea pig for this project was it played Mexican music in Reno, Nevada. And when I saw it on Craigslist, it was $250, and they said, come get it. And when I talked to the gentleman who owned it, he's like, yeah, it's no big deal. It's at a remote transmitter site. You just back up your trailer and come grab it. So I got a bunch of my friends together, we backed up, and there was all these boulders around the transmitter site. And they're like, well, that's theft deterrent. I'm like, well, what's the unload deterrent? How do we get this out of here? So a couple lunches later, my friends agreed that they weren't mad at me anymore because it took a lot of time and effort. We pulled all the magnetics out. We had a wagon to stably, on some plywood, move it out and get it to the truck. But we got it home in one piece. And so that was my first exposure, and now I've got 6 different broadcast transmitters that I've been acquiring when they're free or cheap on the internet, because I really think that there's potential for these, and they're a piece of history that's a lot of the time going to the scrapyard because there hasn't been an easy way to use that for something other than commercial broadcast service. So bringing that into my education, my master's thesis, I was able to tie that into working on the broadcast transmitters. So the goal of the thesis was to design and develop a system for converting and controlling broadcast transmitters for amateur radio use. use. And there was a lot of hurdles that we wanted to overcome there because setting a BC1T in your ham shack is really not possible or practical. So size alone, then there were some functional and operational components that we needed to address. And the goal at the end of it was to create a replicable and modular system for broadcast transmitter repurposing. So each transmitter's internal components are going to be different. Any changes to the final and tank circuit may be slightly different, but we wanted a system for the actual control side to be something you can put on your desk in your ham shack and remotely control.
Are these transmitters three-phase?
Most of them are single-phase 240. Yeah. Mm-hmm. At the kilowatt level, single-phase 240. So here's the specification. So great timing to ask that question. So this right here is some of the specifications of the BC1T, and I apologize that it's pretty small for some of you further back, but the big things I'll be reading off anyways. So the relative output power is going to be 1,000 watt or 250 watt. So that was a selectable change on the BC1T for nighttime operation. When it got to nighttime, you cut it down to 250. Your propagation is about the same either way. And then back to daytime, you flip it to a kilowatt. So the frequency range these were designed for is 540 kc to 1600 kc, and that's because that's the AM commercial broadcast band. So it's developed to really operate in that frequency range. Going to 160 meters, you can do that with pretty much no modifications to the actual tank circuit. 80 meters, you're talking probably capacitor changes, nothing major. 40 meters is possible, but it's a little bit more intensive. So I believe AWR Labs did a write-up, and Tim Tron?
Yes.
Okay, appreciate that. And so they took a BC1T as well, and they did quite a bit of conversion work, and they documented some of that on YouTube, which is a cool video. If you look up AWR Labs broadcast transmitter, they go over some of the changes that they did on that unit. But that was still a crystal controlled unit, which is different than what we're going to be talking about here. So when running a system like this, again, we can get 160 with pretty much zero modification on the frequency, the tank circuit assembly side. Power input, 240 single phase. So this is something that really is meant to be a garage build kind of thing. It's pulling less power than a Tesla charger. So it's practical to put in your house, in the garage, but it's really not practical to put in your ham shack. You probably don't have this kind of current capacity 240 access inside of your shack. So audio input is another thing I want to touch on because that's something that we had to address. So they call for 12 dBm plus or minus 2. So this is something that we needed to come up with a way to amplify our audio input so that it can meet the requirements of what the transmitter is expecting. So to put comparable cost, so to get a kilowatt on a, you go online and buy something, to get a kilowatt output, you're looking at $4,000 for an amplifier. Now, there's significant benefits to this that the broadcast transmitter doesn't have because this is meant for all HF bands. You're really not going to get all HF bands out of a broadcast transmitter no matter what you do. But just to kind of put into perspective a little bit, if you have your transmitter or your transceiver now and you pump it into this, you're looking at $4,000 to get a kilowatt. Our estimated cost for the entire system for all the retrofit work and the transmitter itself, the biggest variable here is what you pay for the transmitter. So if it's free, like a lot of them are, then you're on the low end. I estimate up to about 500. You can usually find something in that price range. There's some that are more, but just to put that in perspective. So we figured $300 to $500 for the transmitter. The material for the console construction, so we had Front Panel Express actually built the panel based on our design, so that was the most expensive part. All the other parts and pieces and hardware were not as expensive, but we estimated about $200 was spent on that. The audio filter and amplifier parts were about $60, and those were all surface mount based on a PCB we put out there, so that's total loaded cost of what it took us to build it. Power supplies were about $50. Frequency control parts were around $30, and then conversion components for the LC tank circuit. Again, this is going to be very variable depending on which transmitter you do it on, but $60 was about the estimate of what it took to do it on that BC1T when we did our calculations. So significantly less kilowatt, cool looking amplifier, if not full kilowatt transmitter with tuning. But broadcast transmitters aren't great as ham radios as they come. So the real three pieces that I'm gonna hit on today on what we accomplished with the console and with the project in general are frequency control, having a way to actually tune in, line level audio input system, so providing that 12 dBm, and portable modular control console, so having something you can have on your desk to run the radio. So frequency control was the first part that we wanted to address. So right now, the original system that comes in these broadcast transmitters is usually of this 50s, 60s vintage, an ovenized crystal. So you have temperature regulated crystal, and that gives the transmitter a plus or minus 10 kc stability on the frequency side. So that's great. That's awesome for when you have a fixed frequency and you know every single time that's where you want to be because you're a commercial service broadcast station. For ham, that's not as great. If you want to contest, if you want to change nets, crystals are getting extremely expensive as it is, and you have to have one for every single frequency that you want to tune into. So new net opens up, you don't have that crystal, oh crap, you can't do anything about it. So what we did with this system, at the time, the FCC allows for 20 hertz of drift. That's the maximum that you can have one way or another from your center frequency on an AM broadcast station. And at the time, the ovenized crystal was really the only way to do that. If you used a normal VFO system, and we have some drift data I'll be showing here as well, that frequency stability really isn't guaranteed to be there. And we actually saw in our testing that it may be there sometimes, but it's not always there consistently across temperature ranges and stuff like that. So today you can get very low cost, very accurate synthesizer systems that you can then integrate into some of these frequency control systems. So the Scilabs 5351A is this chip right here. This is the surface mount version, and this provided extreme accuracy for a fraction of the cost of what it would take to even buy a used Johnson 122 VFO. So let's go here. Here's the stability chart for the ovenized crystal system from the Gates BC1T. So this shows that from 20 degrees centigrade to 60, the stability of these systems is within plus or minus plus 10 or less and minus 5 or less there. So this is how they made sure they were on where they needed to be. And that was the only way to do it at the time, reliably and for a reasonable cost and reasonable design. So to compare that, because I wanted to see really how bad or how good is this compared to what they could have done in the 60s. So the 122 VFO is a pretty good VFO for the time. And that was something that we figured if that has reasonable results, that's what we can use as our comparison. So we decided we were going to perform some drift tests. So we have a frequency counter on the bottom on the right, and the signal generator above it was used for some calibration there, and then the Johnson 122 on the left. So what we would do here is we'd use the frequency counter to determine where the VFO is set. And this is kind of an important piece because when the VFO's needle is on 7.0, the frequency counter is not at 7.0, it's 6.95. Sometimes it's way off. So we wanted to make sure that we were using that, and that is a drawback to a traditional VFO, is that whatever that screen reads may not actually be where we're at. So we'd set that, and then we'd let the unit sit in idle for about 30 minutes, make sure it got up to temperature, and then we'd set our frequency again to make sure we're good. We wanted to make sure it got up to temperature first before we did anything. So we set it at a certain frequency, and we tested 160, 80, and 40. And we made sure, okay, where are we at frequency-wise? We take a note of that measurement, we let it idle for another 30 minutes and come back and say, where are we at this point? And that will give us an idea of how far it's drifted. Now, the only drawback to this measurement system is that, well, the one I thought of so far, is that we're not measuring what's happening in between. So it might have went way out of spec and then settled back down. We're not getting that reading as of right now, but that is some further modifications that I'd like to do to this test. So to look at the recordings of what we got, we saw 3 hertz of drift at 40 meters. We saw 2.5 hertz of drift at 80, and we saw 17 hertz at 160. So these numbers on the surface don't really look that bad. Again, there's some other components that may not be figured in here, but this is in ideal conditions where there's no temperature change, it's a laboratory environment, and we know for sure that nothing's been moved, bumped, shaken, anything. So this is reasonable. We could use this VFO, but the Scilab's synthesizer data, 5351A, goes by less than 1 hertz throughout our entire measurement, and the accuracy for the data sheet is 0 parts per million. So this is something that I figured was a great way to do it. It's under $30, and again, to buy that same VFO is probably 70 to 100 now on eBay. So we went forward with that plan. So we based a lot of the frequency control on an article by Bob Fontana, AK3Y, and this was from the December 2020 QST. He won the cover award that year actually for this article. It was very well written. And what he wanted to look at was creating a synthesized QRPP transmitter. And you can see there on the right, the units on top of that S-line columns. So we wanted something, the frequency control is the real key here because the synthesizer has an output. But the synthesizer output can't go directly into the radio, and we need a way to tune it, and we need a way to see what we're actually doing. So what we did is took a lot of the inspiration from this article. So we used an Arduino Nano, which is an off-the-shelf, few dollar microprocessor there, and this 5351A synthesizer. We used a rotary encoder, which you can kind of see on the front here of the console, and I have a better picture later of the console because I know some of you may be struggling to see from that far away the details there. But the rotary encoder gives us the tunability, and then we have frequency displays as well. So his goal was to create a super stable and cost-effective frequency control for QRPP and low power consumption. My goal was get something that we can plumb into the broadcast transmitter and have tunability. And it actually ended up working out with the same benefits. So the synthesizer offers full tunability across the entire band, but it also offers multiple band tuning, which is huge because now we can just switch over bands by pushing a button. It allows us to have resolution as low as we want. The code was pre-programmed for 10 hertz and 100 hertz increments, but that can be changed to 1 hertz increments, and can be changed to 0.1 hertz increments. Whatever we want to do, that's just a software thing. It's very easy to change. It's a cheaper option than individual crystals, so again, desirable crystals I've seen on eBay are $20 a piece. And when they wrote this article, the whole system was $20. It's about 30 now for all the parts. But this gives us a way to do that and have whatever we want for one cost. And then the displays are really huge too. So the accuracy of the VFO's display versus the accuracy of what this OLED displays is significantly different. We know for certain that's where we're at on this display. With the VFO, we've got our fingers crossed that it's where it's lined up on the needle. So going into the audio input system, so again, we need 12 dBm to have the audio line level that we need for that broadcast transmitter. So originally, when these were in commercial service, the station would have a console like this, and there's a lot of drawbacks to this for a ham shack. One is that it's huge. These are like 3.5 feet wide, and they're like 80 pounds, and they have 8 to 16 inputs, which is not necessary. So, and they're hot boxes, they cook. So this is not a great way to do it. While it could be used, it's not really something that makes sense for the ham shack side. So the answer was, well, how do we design an audio amplifier and filter circuit so that we can actually control the line level like this does? We can have a spot to plug in our microphone. We have a way to monitor our audio level, but don't have an 80-pound yardstick sitting on a ham shack. So that's where we kind of got into this design. So this is the audio preamp and filter circuit that was designed for this project. And it's built a lot around this amplifier in the middle, this INA 163. So I'll kind of walk through this as it's drawn here, but most of the circuit on the top side here above my mouse is based on the app notes from the INA 163. So we allow for, on the very left here, we can either have a balanced input or a single-ended input. And we also have the ability to have phantom power if we have a microphone that requires that. So our microphone inputs will come in and they'll go through this INA 163 instrumentation amplifier. So this instrumentation amplifier is, again, the heart of this because it's providing extremely high gain. So it's capable of 105 dB of gain if necessary. We don't probably want that all the time because we want to make sure we're providing the right level for the transmitter, but it can do it. So in this circuit, on the feedback side right here, we put in a fixed resistor here to set the maximum gain at a limit. And because this INA 163, if there is no resistance here, because we used a variable resistor below that potentiometer, if that's set to 0 and there is no fixed resistor, it becomes an oscillator, and we don't want that. So we set the maximum cap with that fixed resistor, and then we allow for tunability from there, from about 105 dB to 0. And so once it goes through this circuit right here, it actually passes down and goes through our kind of modular filter assembly. So we chose to use a Salem key filter and bandpass configuration here, and we set the limits here between 200 and 4 kC. So 200 hertz and 4 kC. So that's what we figured would be appropriate. Those values can be changed easily depending on what's necessary, needed, desired, but we wanted to trim it down. And that was one of the things, the broadcast transmitter is built for as high a fidelity as you can squeeze into the legal limits, not necessary or legal for ham operation. So we wanted to make that a little bit finer so that it was more appropriate for the application we were using it for. And then after it goes through our filter, it comes back up, and this chip right here, which is the SSM 2142, it provides a balanced output. So we have our single-ended input, we have balanced output to go into the transmitter. All right, so these are two of the PCBs that ended up not being used for the project. And I wanted to highlight this because this is really a learning experience as we go. So with both of these boards, there were issues that we didn't originally plan on. Everything looked great on paper until you plug it all in and it doesn't work. So we prototype all this stuff the best we can. We run it through simulators when we can, but sometimes it doesn't work. So we go back to the drawing board and figure out a better way to do it. And that's been kind of the theme throughout a lot of this. And I know for a lot of people who have homebrewed stuff and made stuff at home, it happens. And you go back and figure out how to make it work from there. So some of the key takeaways on the audio input side. Again, we designed this to have a fixed resistor to make sure that this INA 163 didn't become an oscillator, because that would really be a problem on our audio input side. And we wanted to make sure that we had control so that we could make sure the audio input's not just as high as we can get it. We want to make it a value that's appropriate. Just because we can crank it all the way up doesn't mean that's good for what we're trying to use it for. The Salem key filter design, that's something that was kind of, in my opinion, the best fit for the problem, but maybe there's other ways to do it or better ways to do it, and we're playing around with it more and more to see better ways to optimize the system. But this provided us with a pretty straightforward, easy design, something we could do on surface mount pretty easily, and get the fidelity that we wanted while still staying within the amateur limits. And yeah. Okay, so the third piece that we really wanted to take on here with this project was the console itself. So the size of the broadcast transmitter and the 240 volt requirement and the heat and the noise, these are all things that mean you don't want them inside. So how do we get something so that we can control the transmitter as much as possible from our desk? So in order to be functional, you need to have a couple different things at your disposal at your desk. And that's connectorization for microphones, that's audio level control, that's forward and reflected power information is cool. That's something we chose to put on there. A way to key it, a way to spot it. Those are all things that we want to make sure were available at the desk side. And then one of the things, and I have a slide a little bit later where I talk about some of our future considerations, but I would like to have a way to remotely tune the final assembly on the radio. That's something that would be a big benefit. It probably won't fit on this console, we're pretty stuck as it is, but an auxiliary console to do the remote tuning with servos. The drawback there is that each transmitter kind of has a different scheme, so it might not be a direct, this console will work for all the radios, and that's something we've been playing around with on, can we do it, and if so, how? So here's the console, for those of you who might not be able to see it as well from the back. So I'll kind of walk through what these pieces and components are here and what they're being used for. So top left, we have our reflected power meter, and I'll tie that into the top right, which is our forward power meter. So we're using a directional coupler, and it can be as simple as one of those out of the heat kit power meters from back in the day, that those work just fine. But we have a signal there where we can pull in and measure our forward and reflected power from one of those directional couplers. We have our audio level meter in the middle, and that's taking, again, going to be based on the gain that we're setting with that variable resistor on the INA 163 that's been pulled out to the front panel here, which brings us down to our audio level meter. So that's the variable resistor, that's the potentiometer that we're using. We have down here our mic jack. The original design of the front panel just put a small hole there, so that way whatever was desired as far as microphone connectorization could be used. We used a tip ring and sleeve, but it'd be just as easy to put a 2-pin connector there or whatever you'd like to use. We've got our power switch next to that, so that turns on our AC power that goes into the console. Powers up all the power supplies, Arduino, the relays, all that. We've got a frequency spot switch, which that gives us the ability to key up just the clock on the 5351A without turning on the transmitter, so that way we can zero beat our receiver in and make sure we're where we want to be. And then I'll kind of step up. So there's a hole that says step, so that's actually a button. It's a momentary switch that should be used for changing the tuning rate on the Arduino system for frequency control. So as I said earlier, we can change between 10 hertz and 100 hertz increments. That's how we change between those. The OLED display is under frequency A and frequency B. So the original Tunatin S script was written so that you could actually run 2 separate Arduinos and you could run 2 separate frequency controls. So the reason that you might want to do that ties into the system select switch to the right, because this system was designed to have 5 different transmitters all hooked up to it. And that system select switch is a huge band switch, relatively, that's changing all of the wiring of this system to move from one radio to another. So that way, with no changes besides turning the switch, we're moving our metering to a different radio. We're moving our connectorization for the microphone to a different radio. For our audio level, it's going to be fixed, so that one won't move. We're moving our frequency control to another radio. So if we have our BC1T, and we have that one set up for 160 meters, but on the BC250, it's set up for 80 meters, and it's all tuned for that on the final side, we can just switch over right there. And that would give us the ability to do that very quickly and very easily without having to go back out, reset everything, and change it. So that's the reason for 2 frequency controls, because that was a question we've gotten before. We have, so the incremental encoder is right in the middle, and that's how we do our tuning. The one drawback that I've found so far in this design is that when you have 2 set up of the frequency controllers, you're tuning them both, which is kind of inconvenient. So a future consideration would be a switch to switch that back and forth. But it works how it is, just not how I like it. We have a micro line audio switch, so that's a future consideration for having a line audio connection in the back. There's terminations for it on the back, but there's no connectorization as of yet, but there's a switch to change between those. We have a TX key switch, so that's how we can key up our transmitter if we want to tune it. There's a switch right there, fire it up, see what we got. And then we have a telegraph key plug, and that's, at this point, kind of a future consideration as well. For each transmitter, you need to find a way to key it without hammering the power supply each time that it's keying. Because we don't want to just key it on the plate side and beat it like that. They are continuous commercial service radios, but that's not the best way to handle the transformer. So it's there, each transmitter you have to figure out how you want to key it for that. So here's the kind of block diagram of the console, and this is going to focus on that system select switch. So what we can see here across the middle is these are the things that are being switched by the band switch. So we have our audio level is there, and that's going to connect to whatever radio is passing through. Our push to talk is going to move. We've got our key switch there. We've got I'm trying to go in order here. Manual transmit, forward RX, forward power and reverse power. So all those are going to be switched along that cycle with the system select switch. And what's shown here on the top is the terminations. And so I believe that's perfect. That's our next slide. So tying it all together. So on the top right picture, you'll see 5 different white terminal blocks. And so the goal of this was that from the transmitter, where you pipe in these different commands or these different connectors is going to be a little bit different. The concepts are going to be the same, the goal of them is the same, but where it connects is going to be different, how it connects is going to be different. So the goal with this was to have a very well-defined terminal block for each system. So that way you find it on your broadcast transmitter, you plug it in where it's supposed to go across this terminal block, and now it works how you're expecting it to. So there's 5 there, and then if we go to the bottom picture, so there's that system select switch with the yellow wires coming off of it, and then there's actually a terminal block right here, which is our hidden number 6. So that's where all these connections are being made from the switch to those terminal block locations. So all the signals that we're talking about will go into that, and then they come out of that and go into the switch, and then from the switch will go to your 5 different systems that you can select. So we wanted to, again, when we're building this, we're looking at ways to make it easy to build. You don't want something that you need a bunch of specialized tools and equipment for. Want something that's reasonable size-wise, fit-wise. This is rack mountable, so if you want to put it in a cabinet, you could. If you want to put it in a rack, you could. But it's also built to kind of just sit flat, like it is right now on the table. So if you want to just set it on your desk, it works. And we built it with bracketry to mount all the power supplies, all of our connectorization, and have a way to plumb that all in. If you have this full of wires, it's not something where the wires are making it not sit right, not fit right. It's built to be pretty well-rounded for going wherever you want to put it. So harnessing, so again, kind of touched on this. This is what the that system select switch and all those harnesses looked like before we got it all mounted. So went from rat's nest to pretty clean, if I say so myself, with how we were able to mount it all and plumb it all in here. But it was really a big deal to make sure that that system select switch did more than just switch one thing to the transmitter. It switched everything. When you change that, you completely isolated the one transmitter that you switched from and completely integrated the transmitter that you switched to. So plans for future improvement on this. So this is actually one of the tuning assemblies within that RCA pre-World War II broadcast transmitter. So that's significantly different from the gates. And I have an okay picture of the gates coming up in the next slide, but how you tune these is going to be different radio to radio, and especially on the radios like the RCA where there's an exciter and a final amplifier where you have 2 sets of tuning involved. So I'd like to look at, and I've done a little bit of research on this because it's something I'm interested in, but can you have a servo-based system that can do that tuning? How do you mount that? You know, when you're turning one of these big roller coils, or even when you're turning some of these older capacitors, there's a lot of torque you have to put on that to turn it. It's something you use kind of your whole arm to turn. So servo systems would have to be bracketed, and they'd have a pretty high power consumption to do it. So there's a couple of considerations that have to be taken into account, but something I like to look at doing. So that way you can just sit in your shack and not have to go at all out to the transmitter itself to get it all running and going. The other part was a remotely controlled antenna tuner to optimize forward power. So this tells you, hey, I've got reflected power that I don't want, but you can't do anything about it from the desk. And when we look at our radio in the shack, it's a lot easier to have an antenna tuner piped in between the antenna and the radio. when my radio's in the garage and I'm in the house, it's not as convenient to be running all the antenna harnessing there. It was kind of a huge benefit that we could just run the antenna straight into the transmitter outside, control it from here. So that's something that I wanted to look at a little bit further to see, can we create that system to kind of piggyback with this? And then a little bit of, I would like to do some further testing on one, power consumption, which I don't think will be too much change, but audio output levels and quality compared to the original broadcast transmitter. So taking the original audio amplification system that's in there, comparing it to this one, and looking at distortion values, looking at what the waveforms look like between the non-converted transmitter and the new design audio input section. So this is, again, unfortunately, they're black and white in the manual. I wish I could have gotten a better picture inside of the BC1T at the house there, but this is, the tuning assembly is shown up top there with the roller coil and the capacitor behind it, which you can't see. So just to show the difference in the tuning side and what's required when you start looking at remote tuning capabilities. So again, want to thank my grandpa Gopher. He's back here, KE6F. He's helped me a lot on this project and utilized a lot of his knowledge and experience working on this. And my thesis advisor, Dr. Melissa Markovich, who's helped me pursue my ambition in ham radio and doing all the fun stuff and getting credit for a piece of paper. So that's what I've got. Thank you, everyone. Any questions? Yes, sir.
I never heard you mention electrolytic capacitors. Have you been lucky?
With which side? On the broadcast side?
Yeah.
Transmitter side?
Yeah, I mean, not having to replace them in 80-year-old 60-year-old transfer.
I fired up most of them, and they've been okay so far. Luckily.
Old oil filled caps.
Is that what they are?
They're old oil filled.
Ah.
They last forever.
Yes, sir.
So just interested, you said you had some, on your PC boards, you had a couple different roles. Can you just talk about some of the issues you had? Not being judgmental, but just.
Yeah. So I
And
showed
also,
them.
what's your power bill like?
That's why.
So one of the ones, and my grandpa said I should have included this, I probably should have. One of the ones, we were cutting the actual board. So on the board manufacturing side, we use PCB Express is one of the ones that we've used. And there's a certain size, the minimum size. So we'll try to put a couple different boards on that one board so that way it's cost effective. And we were cutting it with a little diamond saw and the cut kind of a little bit crooked and cut right through it. But that's not a design issue, that's just a handling issue on our side. Going back to these ones, so let me go back to that slide. So one of the problems on this one was that we originally only accounted for a high pass filter, and then we started looking at what it looked like on the audio analyzer, and it wasn't great. So we ended up redesigning to have the Salem Key Butterworth band pass filter. So that was one of the issues. On the other one, I think it was we didn't have the capacitor on that one, right, Grandpa?
Yeah, well, one of them had a relay-driven 20 dB pad, but when you fired the relay, it put a big swipe all the way through the audio chain. Some of the stuff Justin and I worked on earlier was for a guitar amplifier, and this is the outgrowth of that, was up for a mic preamp. That was the problem with the first one. Then of course the second one, it only had the one filter as opposed to the cascaded filters. So they're in the trash can. Just it was, I guess you call it an $80 experiment, but that's the cost to run one of these boards. But they're very fun to work out and design. But I'll leave that up to Justin now.
It's an $80 learning experience.
Yeah. Everything's a lesson.
That's right.
And the power bill is not great in the summertime.
How long did it take you to, from beginning to end, to complete the design and manufacture?
We've been working on this since about 2021, I think, pretty heavily in and out. And it's been kind of a side project. Work full-time, school part-time, and hobby extra part-time. So it's been kind of a 3-year project, more or less. The broadcast stuff we've been collecting since about 2018. So we've had the stuff sitting in the garage, and it's like, this is so cool, we should do something with it. And powered them up and sat there and stared at all the tubes lit up, and then said, what are we gonna do? So that's I wanted to do it, this was the opportunity to do it, and have a good reason to do it too. And so, yeah, so broadcast stuff, longer, but the console and the thesis, about 3 years. Yes, sir.
You never said, is this a high-level transmitter for modulation or low-level?
High levels. Yeah, the BC1T is a pair of 833As modulated by a pair of 833As.
Okay.
Yes.
So you never mentioned how many QSOs you've had and whether it's been.
We haven't had it on the air yet, so we're still addressing some of the small problems that we're kind of ran into as we go. One of the things we ran into recently on the Tunatin-S based frequency control, we built a little proto board that the Arduino actually mounted to, and that gave us connectorization. So when Bob Fontana did it, he just used wire connections on the Arduino itself. We wanted to make it a little bit easier to have it mountable back here and harnessed. And on the actual integration board there was a little bit of an issue with the circuit design. So that's been kind of a hold up at the moment. So I haven't had a chance to fully run it yet, but we're pretty close. Feeling pretty confident. Yes.
A follow-up to his first question, about what power level, typically, generally speaking, would three-phase power start becoming an issue?
Probably in the 5 kW range is where you want to be at 3-phase, and they'd probably be on 480 at that point.
Okay.
Because this one, I mean, I think that what they're calling for is 4,000 watts of power consumption at 240. So you're looking at, I don't know, 18, 17 amps. When you start getting above 20, they start wanting to step it back up and get something else. So I'd probably say in the 5 kW or 10 kW range is where they want to be at 483 phase. But that's where the kilowatt transmitter is really the sweet spot. It gives pretty much max power for AM, and it gives you 240 single phase, which you probably can get access to at a house level. Yeah.
Well, you really won't be running that transmitter at a
You better
kilowatt.
not.
You
Yeah.
better not run that
It's
at a
not
kilowatt
legal at
carrier.
full power.
Yeah, you're gonna be running it at a fraction of that.
Yes.
Like,
The
well,
250 watt level is probably about right.
that's about
Yeah,
right.
yeah,
Or,
yeah.
or 375 if you've got
Yeah.
a bigger transmitter. Yeah,
Mhm.
so your power consumption isn't quite so bad.
Yes.
Yeah, I run a couple of these too.
Oh,
so,
cool.
yeah.
Awesome. Yeah, my T368, which I think was in one of the earlier pictures, that's about 375 watts.
Yeah.
And that pretty much puts you at legal limit.
Yeah.
Yeah.
If you're running 100% modulation.
Yeah, it's cranked. Yeah.
So,
Cool. Thank you, everyone. I appreciate you coming to the presentation today, and hope you enjoy the rest of your Pacificon.
Thank you.